Hello, my name is Jeanneret and I'm a Senior Scientist at Intertech Melbourne, and welcome to this presentation on plume velocity characterisation of pressurised metered dose inhalers and soft mist inhalers. Today we'll focus on plume velocity and touch upon force to actuate. Firstly, I'll briefly describe why these techniques can be useful for in vitro bioequivalence and development. Then we'll take a look at how we measure plume velocity, the work performed here at IM, and finally a look at the conclusions from the study. So why is plume velocity important? Plume velocity is defined as the rate at which the leading edge of the plume fired from a device moves from the actuator with regards to time. Various techniques are used to measure aerodynamic performance, and historically we have focused on aerodynamic size and shape, but newer techniques such as spray pattern and plume geometry can help give a greater understanding. Along with this, aerodynamic performance is also directly related to the velocity of the emitted spray. Thus, plume velocity can be a powerful tool to help characterise the drug-device combination. Therefore, expanding our understanding of the aerodynamic performance can help measure the efficacy deposition of drug into the lungs, and thus the more data we have available to assess aerodynamic performance, the better. When developing a generic product, the generic product needs to demonstrate bioequivalence with respect to the reference product. Using an in vitro only approach to generic nasal products with regards to bioequivalence and a weighted evidence statistical approach has been previously successful. In recent guidances for aerosol products, the FDA have included plume velocity and force to actuate as additional supportive in vitro studies to provide evidence for bioequivalence. Now we shall talk about how we measure the plume velocity using the Pressurised spray view. The spray view is used for measuring and analysing the spray pattern and plume geometry produced by a spray and aerosol generating device. As previously mentioned, these are ways to measure aerodynamic performance. Time-synchronized images calibrated with relation to distance from the mouthpiece are produced using a high-speed camera and a planar sheet of laser light. Along with this, the automated actuator has the capacity to determine force to actuate by measuring the amount of force required throughout the duration of the actuation. So the spray view can be utilized to characterize both plume velocity and force to actuate. Plume velocity is a novel approach using established techniques of the spray view. As mentioned, the spray view produces time-calibrated images, and thus the plume front can be tracked from the moment it first emerges from the orifice to the moment it leaves the field of view. This allows up to 100 mm of plume to be captured. The velocity can therefore be calculated from plotting the distance the plume front has travelled against time, and the resulting gradient is the plume velocity. The following example of plume front velocity analysis is for a PMDI device. Firstly, the 0 point is measured, which is the last point before the spray is emitted. An image is taken every 2 seconds by the spray view, and the plume front is selected as the furthest distance in millimetres from the orifice, where the intensity of the plume is greater than or equal to 10. Thus, a second point can be plotted at 2 milliseconds, followed by a point at 4 milliseconds, at 6 milliseconds, at 8 milliseconds, until in this example the plume front exits the field of view at 10 milliseconds, so no point can be plotted. A linear regression can be applied across the points measured, and the plume velocity can be estimated as gradient of the regression line in meters per second, in this case 12.2 meters per second. Having looked at why and how we collect the data, let's look at the work that was performed at IM. The aim of this work performed was to use a novel technique of plume velocity to analyse various PMDIs and one SMI. Overall, 2 PMDIs of the same drug type were analysed that were a generic and reference device, along with one SMI. For each device type, 3 devices were analysed for 3 replicates per device, allowing mean plume velocity, plume duration, and actuation force to be measured. The PMDI results showed slight differences in these means between the 2 products, but are largely comparable. The ranges of the mean plume velocity for the 2 PMDI products overlap. There was also inter-device and intra-device variation within the same products. Further statistical work would be required for bioequivalence analysis. For the SMI device, had a lower initial velocity and a lower actuation force required, which is expected due to the method of actuation. Also, the plume duration cannot be measured as the device is still being actuated when the final image is collected, so no endpoint is observable. From the work performed at IM, various differences between the techniques were observed. For PMDIs, a maximum of 5 points could be measured. and the plume velocity was assumed to be constant across these 5 points. Whereas for the SMI, up to 40 data points equating to 80 milliseconds could be measured, and linear and non-linear regions were required to be selected. The linear region is used to collect the initial plume velocity, as can be seen here. Within the linear region, the plume front can be seen to move across the field of view, and thus the distance the plume front has travelled with relation to time can be plotted, and the initial velocity is calculated via linear regression. The length of the linear region was device dependent and was approximately 30 to 50 milliseconds. However, over time, the plume will start to decelerate in the static air and billow out, which can be observed within the images produced by the spray view. The plume will still be moving across the field of view, but at a slower rate, and these points are not included in the velocity calculation. There are some conclusions to draw from this presentation. One point to make is I have focused on the plume velocity work performed within the paper, but force to actuate is also covered in more detail. Looking at the work carried out at IM, the following graph shows the distance and time relationship for both PMDIs and SMIs overlaid on the same graph. The blue and yellow lines are the PMDIs and the red is the SMI. Using this graph, we can link how plume velocity can be crucial to patient compliance. The first point to notice is that PMDIs have a higher initial velocity of the device, and this has been previously mentioned. For PMDIs, the synchronization between inhaler actuation and inhalation is extremely important and relies on sufficient training and patient compliance in order to maximize the efficacy of the treatment. A faster velocity may make this harder to achieve. The second point is the longer duration of the SMI, where the plume front stays within the 100 millimeters of the field of view for a greater duration. As previously mentioned, SMIs have a lower initial plume velocity and this longer duration, which means there is less of a requirement for synchronization, so less training is required to use the device, and increased patient compliance leads to better drug deposition within the lungs. Additionally, those who would be at risk of decreased clinical efficiency when using a conventional inhaler will receive a greater benefit from using an SMI. Finally, the SMI do not show a constant velocity, as mentioned, due to the deceleration in static air. This first occurs after approximately 30 to 50 milliseconds after the plume formation. In conclusion, the mechanism for aerolization has a major effect on the plume velocity. The HFA propellant-driven PMDI devices have a considerably higher velocity compared to the mechanically driven SMI devices. Both plume velocity and force to actuate have been highlighted by the FDA as effective in vitro characterization techniques for a weight of evidence approach to determine bioequivalence. IM have successfully analysed 2 PMDIs, which were a test and reference products, and 1 SMI. The PMDI devices gave comparable data on a limited data set. Plume velocity could be a useful tool in development, along with the standard characterization techniques to assess aerodynamic performance. An example of this is the shift away from the use of HFA propellant in PMDIs, and plume velocity could be used to help assess if any change in aerodynamic performance due to the use of this new propellant. Thank you very much for your time. Please feel free to contact me if you have any questions about today's content.